Let's look at some synthesis strategies now using alpha carbon chemistry. As we've seen in this chapter, there are many C-C bond forming reactions that we've discussed. Some of them produce two functional groups. And if we observe the relationship between those two groups, we can get an idea of which of these C-C bond forming reactions we used. So let's look at first the aldol and Claisen. So the aldol in its simplest form gives us a beta hydroxy carbonyl species. So of course you can see that there's a 1:3 relationship here with these functional groups. And of course we know if we add some heat to this mixture, we can make the alpha beta unsaturated carbonyl. So if you ever see anything that is an alpha beta unsaturated carbonyl, or could have been at some point, that could have come from an aldol condensation. I would like to point out that this is a good Diels-Alder dienophile now that we can use in subsequent syntheses. We can also use it for conjugate addition. Let's look at the Claisen reaction. With the Claisen reaction, we produce an ester with a beta ketone. Also, keep in mind the 1:3 relationship in this case. So this is called a beta keto ester. So whenever you see a beta keto ester or something that could have been a beta keto ester, you should be thinking about the Claisen condensation. Let's look at an example where we have a 1,5 difunctionalized compound. So the Stork-enamine synthesis. First step, secondary amine to make the enamine. Second step, add a good Michael acceptor. That's basically an alpha beta unsaturated carbonyl compound. Third step, mild acid workup. And we essentially add, in this case, 4 carbons to our original compound. Let's look at the functional groups. So we have a 1,5 dicarbonyl species. That is a good indication that we have used a Stork-enamine synthesis to produce that 1,5 dicarbonyl species. So if it's a 1:3 relationship in the functional groups, probably an aldol or a Claisen. 1,5 dicarbonyl species. Most likely we used a Stork-enamine synthesis to make that compound. Let's look at a couple examples. What if we started with this compound and we got to this compound? A seemingly much more complex diol. Well, let's look at the functional groups here. There's a functional group there. And we see that on the third carbon, there's another functional group. This is a 1:3 relationship between the functional groups. And as I've been trying to stress all semester, an alcohol is essentially the equivalent of having an alkyl halide, an alkene, carbonyl in that position. It's just one step removed from it. So we have 2 alcohols. So we could certainly envision these 2 alcohols having come from maybe 2 carbonyls or 1 carbonyl and an alcohol. But let's think about this a little more here. What if we had this compound, right? That's looking more like the Aldol addition, where we've made this bond, turned one of our aldehydes into a secondary alcohol, kept the other aldehyde. And we can envision making that from 2 of these 1-propanols simply via oxidizing the 1-propanol and then doing an aldol addition. This would be an aldol addition. And then a reduction with sodium borohydride. So here's a little 3-step sequence that takes this primary alcohol and extends the chain, doubles the chain in fact, and leaves us with 2 alcohols that we can do chemistry with if desired. And we started our analysis by looking at the relationship between the 2 functional groups. They had a 1-3 relationship that indicated that most likely we created one of these, or the new carbon-carbon bond, which is between carbons 1 and 3 in this case, via an aldol addition reaction. Let's look at another possibility. Let's say our goal is to create this compound. So here we only have 1 functional group, right? But we do have an alpha position. So maybe this bond has been created via an aldol. Maybe this bond was created via a conjugate addition. Remember that aldol condensations create good Michael acceptors, so we can then add a group to the beta position. And maybe this was created via alpha alkylation. So we might have 3 groups here that we've added to our original carbonyl species. So let's see if we can set that up now. There's my methyl ethyl ketone, and if I hit it with LDA at -78, I can probably deprotonate at this carbon a little bit more selectively than at this carbon. That would give me a nucleophile that I can then react with the appropriate electrophile. I think I'm going to do the aldol first so I can get the alpha beta unsaturated carbonyl. So this 4-carbon piece that I've circled probably needs to be the aldol electrophile. So that really is just an aldehyde like that. And if I heat it, I should be able to achieve the aldol condensation product. And now I can add my Michael or my cuprate group. This piece that I've circled on the left side has added to the beta carbon, which is, let's mark these a little bit more clearly. This carbon here is the same as that carbon. So you can see that this 4-carbon group has added to the beta carbon, and I can add that via a butyl copper lithium species. And that's going to give me, let's just look at what that intermediate is before we do anything else at least. By this point, you know that the intermediate in a conjugate addition at the purple dotted carbon will leave us with this enolate, right? We're going to push electrons off of the purple carbon onto the CC bond here, pushing electrons onto the O. So we get an O negative, we get a new pi bond here, so we have an enolate functional group. We've added our new carbon group at the purple carbon, and this enolate functional group can be reacted directly with whatever alkylating agent we want to put onto the alpha carbon. This carbon can be alkylated directly now, and I'm going to do that with simply methyl bromide. So I can choose my nucleophile to add at the beta position, then I can choose my electrophile to add at the alpha position via essentially working up this enolate. This is a good nucleophile. I'm giving it an electrophile, and I can add that carbon. So you can see how we've taken this starting material and we've greatly increased its complexity via 3 different carbon-carbon bond forming reactions that we learned about this chapter. And so what I want you to look for, I'm going to erase these circles now. I want you to be able to recognize when we have an alpha carbon, this one, that has been connected to other carbons. But essentially we're creating this CC bond via an aldol addition or aldol condensation. And then we have the ability to add other carbons to that alpha position as well via alpha alkylation. And say we could add these parts separately, one of them in an aldol condensation, the other one in a Michael addition. So we should start to learn to recognize those when we're faced with a synthetic target.